Hello everyone, thank you for being here. I would like to start with just a simple fact that the sky we see is actually a lie. So what we see is in the past because the speed of light is finite, so everything we see is slightly in the past. The delay can be seconds, minutes, days, years, and more. Also, sunrises and sunsets are fake because the atmosphere reflects light so much that when you witness a sunset, the sun has actually set below the horizon for several minutes. So you're looking at an event that already happened previously. In the northern hemisphere, we have a star that we call the pole star, and we think it's at the celestial pole, where it looks like the sky is rotating. But it's not exactly there. And in fact, the celestial pole moves in space across time, across many years. But thousands of years ago, another star was way closer to this point. So the pole star is the pole star just temporarily. And finally, even a day is not 24 hours. The Earth rotates in 23 hours, 56 minutes, and 4 seconds. What we use every day is called the mean solar day, and the actual solar day is not also 24 hours. It changes across the year. So now let's say I want to build the software with accuracy. Good luck to me. All right, I'm Rémy. You can find me online with the handle Hannequin almost anywhere. I'm a software developer at Thoughtbot. Thoughtbot is a design and development consultancy. We help teams build and maintain their products while leveling up their teams and processes. We operate from the Americas, but also from the EMEA, so Europe, Middle East, and Africa. I'm a passionate astronomer, amateur astronomer, and as you will see today, I try to combine my passion for astronomy and my love for programming. Don't hesitate to reach out to me after. We can talk about astronomy, programming, funk music, food, anything. All right, today we're going to talk about the challenges of domain modeling and how to code, some code design techniques like object-oriented design and domain-driven design. We're going to see how, or at least try to write some code that is easy to read and to understand, code that can be shared and that enables collaboration. As a prop for the rest of this presentation, I'm going to use Astronomy, which is a Ruby gem that I started working on a couple years ago. It provides astronomical data and events in pure Ruby. It's an open source gem. You can look at it. So far, it provides the position of the major solar system bodies, like the planets, the moon, the sun, but also times for events like rising and setting of celestial bodies, equinoxes and solstices, and moon phases. And in the future, I have big plans with more events, more celestial bodies, and more utilities. I also try to take this opportunity to increase the support of Ruby in the scientific computing. If we compare two very close languages, we have Python and Ruby. The syntax is a bit different, the features as well, but they're mainly very similar. But Ruby is really not known for science, and Python is, and I don't like that. I would prefer Ruby to be known also for that. So with Astronomy, I try to modestly inspire others to contribute so that the ecosystem is more scientific friendly. You can check on tibot.io/astronomy if you want to have a look. And I'm going to take a sip of water if you want to scan the code. All right. So let's start with an example. These are the coordinates of the planet Mars seen from Geneva when we started this talk, so 5 minutes ago. Now I'm going to show you the physical notions and data manipulations that helped me get to this point. You don't have to read the slide, it's a lot of things, don't worry. I just wanted to show you the complexity of going from raw data to coordinates that can be used by a human. We have to deal with different timescales, different definitions of a position, apply the right corrections to the right objects, and finally have some coordinate conversions. That's a lot. That was my own example, but I know many of you work with even more complex domains all the time. So how can we keep up in this situation? That's where domain-driven design comes. Now, just a quick poll. Can you please raise your hand if you already heard of DDD? Damn. Yeah. But can you keep your hand up if you already used it in a project? Okay. Okay. Cool. Hopefully everyone will leave the room with at least some knowledge about DDD. So DDD is a development approach that was introduced in 2003 by Eric Evans in his book, Tackling the Complexity in the Heart of Software. It focuses on creating systems that deeply reflect the underlying business domain they serve. So it focuses on core domain, its logic, its meaning, and we try to build an architecture that reflects it. That's a shift on how we approached software development, because instead of organizing around the code around technical concerns like the database or UI layers, DDD encourages us to structure it around business concepts and processes. We try to move away from monolithic models and technical jargon towards more bounded contexts with explicit boundaries and a shared language. And instead of treating all objects the same way, we try to distinguish between identity-based entities and attribute-based value objects. Another major part of DDD is called ubiquitous language. So I didn't know the word ubiquitous. I will probably forget it in a few minutes, but apparently it means existing or being everywhere at the same time. But what it means exactly is the use of a shared vocabulary between developers and business experts. This is meant to avoid confusion and to have everyone on the same page. In Astronomy, we could think of domain experts like scientists. They have the scientific knowledge, but they don't know how to code, so they need a common language with the developers so that they can build something together. So we try to move away from technical jargon, like we have the object moon state and the method compute, which might make sense to the developers. This is a common names that we see every day. That could make sense in some design patterns, but instead, with DDD, we try to focus more on referring to the actual business concept. So we're talking about the phase of the moon, and the event is exactly a full moon. It's not a big change, but when you apply this constantly, you are building this common language. When can we apply DDD? Mostly when collaboration is important between the knowledge and the tech. So let's say if your business experts can't recognize their own concepts and processes in your code, you might be missing or abstracting too much, missing some concepts as well. But again, only if you want to apply DDD and if this kind of collaboration is important to you. The good news is that Ruby is really well suited for DDD because of its object-oriented nature and its expressiveness. With the use of modules, we can build reusable and composable components, and we can have clear and semantic boundaries. We can use meta-programming for domain-specific languages so that we have code that is more expressive and easier to read. Now I'm going to show you a real use case of DDD in a real project, Astronomy. We can start with repositories. So repositories, they are kind of objects that are here for storing data and entities. They don't have any behavior. They don't do transformation. They just here for data storage. One example from Astronomy is the ephem module. It just loads an ephemeris. An ephemeris, we can see it like a big file of software that has raw data. And then it provides it with no transformation. In that case, the distance between the solar system barycenter to the object in kilometers, but we don't care. It just provides the raw data. Then we have domain services. They are more like service objects. They're here to perform operations. They are stateless. They don't hold data. They're just calculators. One of them in Astronomy is a calculator to calculate the rise and set times of a celestial object. It's just here to hold the logic and the algorithms. And then it exposes the data with a simple but intuitive API. And the object itself is not a domain object. It's more like a value object or an entity that we will talk right after. So we have value objects. These are small but very important objects that are defined by their attributes. In astronomy, they could be mathematical and physical values, like an angle, an instant, a distance. If we take an angle, we can instantiate an angle from any unit, a degree, radians, hours. Then we can extract this data again in different units, or we can apply mathematical function like the cosine function to it. So we're just holding the angle as an object instead of a value in a specified unit. Finally, we have entities. These are objects that are defined by their identity. In astronomy, they are big physical objects. They can benefit from repositories for data, and then they are used by domain services for computing. Let's take Jupiter, the planet Jupiter. The variable here is the representation of the planet at a given instant. From that, we have access to different information as value objects, so that we can write code that is kind of readable. We have the planet Jupiter, we can have this apparent position. From this position, we have the distance from the Earth, and this distance can be expressed in different units, in that case, kilometers. To sum up, this is just, it's not even an architecture, but it's kind of a graph of what DDD is and what we just talked about. As you can see, it's not a complex architecture. It's just splitting logic and data into different kind of objects. So this is usually something we call good practice. So you might apply this every day. So maybe you apply DDD or part of it in your code every day without knowing it. It's kind of a good practice overall. All right, brace yourself. This is a lot of code. I'm going to take my time. I'm going to explain everything. What I want to show you is everything I talked about, but with real code again, to try to show you the different objects, how they interact with each other, and how I hopefully make some code that is readable with, again, this common language with possibly scientists that could be reading this. Or at least I wish one day. So we have ephem, which is a repository. We talked about it before. It loads an ephemeris and provides raw data. Then we have instance, a value object that encapsulates time and that handles different time scales internally. That's the representation of an instant in time. Then we have Geneva, that's us, the observer, defined by a set of coordinates. These coordinates are also value objects. So we have the latitude, which is an angle, the longitude, an angle as well, and the elevation, how high you are above sea level, which is a distance. So that represents us. We have then mass, also an entity. It was generated through the ephemeris with the raw data, and it's the representation of the planet mass at a given instant that we defined right before. From the planet, we have the method observed by that generates a topocentric position. Topocentric means that it's centered on us, an observer on Earth. As you can see, I named it topocentric, and in the code, it's a topocentric object. I'm not doing this just to have a fancy word. It's the actual name of astronomers. So if hopefully one day a scientific would look at the code, they would understand that I'm manipulating before an observer on Earth, a planet, and finally having a topocentric position, which has a real meaning. Just a side note, technically the observed by method does some calculations, so we could make it a different domain service. Just for ease of use, I kept it in the Mars object, just to say that DDD is about giving some guidelines, but it's not a strict architecture neither. Finally, from this topocentric position, we can have horizontal coordinates. That's where the object is in the sky, up and down, left and right. One of them is up and down, so the altitude, how high the object is in the sky, which is an angle that can be expressed again in different units. So from that, we have different objects that interact with each other with this common language. They really represent the astronomical experience, But in Ruby, at least I try some code that could be read kind of in English. I'm not advocating for following that constantly. It's just that for me, for Astronomy, DDD was really convenient. It was really a good fit. Every single object corresponds to a scientific notion. Now, I would like to dig a little bit deeper about value objects because domain services, repositories, and entities that could be seen as regular Ruby objects with just different behaviors. Value objects are slightly different, and they are really a major part of the DDD philosophy. They're here to represent fundamental values and notions, and they're not doing anything special. They just encapsulate a data. They're meant to replace primitives like numbers, strings, IDs, and they're here to make the code more readable, testable, and homogeneous. In Ruby, we have a good example of that, which is time. We can instantiate an object, which is, again, the representation of an instant in time. And then from this object, we have access to the information in different forms. We can have the hours, the minutes. We can have also the number of seconds that happened between the time and a date in the 70s. So it's, again, the value object. Slight difference is that usually with value objects, we try to keep them immutable because they are just values. Technically, the time class, they provide some method that changes the value of time, so it's not a perfect value object, but yeah, I'm nitpicking, I just wanted to say. Value objects are really convenient in formulas or in the code when you try to make values interact with each other because they have value equality. By default in Ruby, we have identity equality, so if you have two strings of the same value, they are technically two different objects. With value equality, the two values are tested against each other. So two distances, 10 meters and 10 meters, they are the same distances, so they are the same objects from a value object point of view. Then you can make them interact with each other. One distance plus one distance equals another distance. And from this distance, you can ask again the data in different forms, whatever you want. It's quite easy to implement your own value object. You just have to include the comparable module and to implement the spaceship operator. This is meant to compare objects with each other and to deal with comparison. And then you can add any method you want. This is Ruby. You can change the method. You can add new ones. You can change the plus, minus methods, the arithmetic method, the operators. You just have to be careful if you do that because, as I mentioned before, if you add two distances, that creates a distance. If you multiply two distances, that creates an area, which is a different physical notion. It's just something to keep in mind if you do that, but that might not be a problem in your code. In Ruby, since 3.2, we have the data class, which is very convenient. It has value equality, and it provides a very simple syntax to create value objects without you having to create the class and all that. Again, some code. I'm going to go slow again. This is real code that I got from an astronomical book to get the altitude of an object based on different units. We don't have to take care of what declination, latitude, and hour angle are. These are just angles. I especially want to show you that because they are angles, they are in different units, possibly in different units. The first ones are in degrees, and the second one is in hours, which it's weird, I know, but it's an angle measure. To not be confused, we named them accordingly with the radians suffix, because later in the ratio variable, we need to use the math sine and cosine functions, which require values in radians. So it's not really convenient, but we need to do that so that we're sure that we're not mixing units and we're having problems. There are spaceships that broke into space because of different measurement units. So we don't want to do that. And in the end, the arcsine method also produces an angle value in radians. So you need to, again, have this suffix. It works, but in my opinion, it's not really readable. It's not really convenient. The final value, if you want it in degrees, you again have to convert it. It's not great. If you use value objects, you have the exact same code, but you don't have to deal with unit conversion. You just have to make them interact with each other. And the value in the end is a value object angle. So you can use it anywhere in your code. You don't have to take care of dealing with the unit conversion because it's just the value angle. Of course, if you need it in a specified unit, you have access to methods to call the value in different units. So in my opinion, it makes the code a bit easier to read, to understand, to maintain, and to test. And about testing, I want to mention that DDD really loves testing because it's just about writing testable code. In Ruby, we have a strong testing culture, in the ecosystem and the community. This is probably because Ruby is a dynamically typed language, so we have to be very careful with integrity. So that's why we make a lot of tests. This is great, but it comes also because there are some flaws. And DDD is just about writing small objects, well-defined boundaries, and testable code. DDD is also a good pragmatic choice if you do scientific code. Because for astronomy, for example, I relied on institutes and organizations that provide data in their own language. DDD helps make a bridge between the data, the code, and the tests. This is a screenshot from the IMCCE, that's a French institute on celestial mechanics. And if you look at the code of astronomy, you will see that the names that I am using are almost exactly the same constantly. This is not to make them happy, it's not to call myself scientist, it's just because it was way easier for me to know what I was manipulating and to test it against real code, real data, so that step by step I could test my own logic and rely on the scientific truth. That helps with integrity and maintainability. Earlier this morning, we already talked about the testing pyramid, so I'm going to go fast. But DDD helps having an approach that is almost scientific. You can, with tests, cover all the range of the information. You start with unit tests, especially for value objects and entities. These are really easy to test because they are tested in isolation, because they have clear boundaries. I'm not mentioning service testing because Ronan said it's not real. Then we have integration tests for domain services and repositories, especially testing the collaboration between the concepts. And finally, we have the scientific validation, which is comparing the results with real scientific data, because in the end, this is important to check that we have accuracy in the end. All right, we are almost done. As a last note, I would like to say how we could apply DDD to other projects, maybe yours. First, you need to identify your core domains in your project. What are the main concepts and processes that are critical to your business? You want to talk to your stakeholders to document their vocabulary and what they use, what they say. This helps understanding relationships between the concepts. You want to map the boundaries of the different parts of your system. Where does something end and something start? Look for natural divisions in the language and in responsibilities. And remember that if you look at your own teams in your company, how they are shaped, often they reflect natural boundaries. So you might have already this kind of DDD boundaries in how your teams are shaped. You can start small with value objects. You look for primitive obsession, like places where you're passing around strings, numbers, IDs. They might represent actually important domain concepts. Don't hesitate to use immutability, especially if they are used frequently, so that you avoid bugs. And if you don't know where to look at, you can look, for example, money, date ranges, emails, phone numbers. All these could be possibly value objects. Try to keep responsibilities simple and separated. Repositories are here to abstract data access. Domain services are for operations. Entities are for business logic. And we talked about value objects before. I know there are many Rails developers. Often we say we try to avoid fat controllers. We have more objects, but we try to avoid also monolithic God models. Monolithic God object models. That was hard to pronounce. So we try to avoid to have big objects. Try to separate everything, clear boundaries, clear language. And don't forget the tell, don't ask principle. So tell the objects what to do instead of asking them information and then act and perform on this information. Finally, don't overthink it. It's just DDD. It's just about making small objects. It doesn't require to have all the building blocks. Just start small with one core concept or very frequently changing one. And remember that the goal is just shared understanding, not architecture purity. All right, let's wrap up. So we've seen how DDD can help manage complex domains and how Ruby with its expressiveness and object-oriented nature can help with DDD. The same way that good software eliminates complex business domains. With Astronomy, I tried modestly to write code that was both functional and educational. And again, I really wish that Ruby with its expressive syntax and object-oriented nature could have a better place in the scientific community. Just to finish, I would like to give a special shout out to Thoughtbot for their support and allowing me and enabling me to work on Astronomy and collaborating with the community like today during investment time. Thank you very much.